You all for staying until today and attending the session. This meeting has been a lot of fun. And as it turns out, AutoCube, really, I've thought of them almost like a collaborator in building the measurement capability I'm going to talk about. So thank you for the invitation. So I want to thank up front the postdocs who worked on this long, arduous process. Many of them, of course, have gone on to other things. It has taken a long time. I also want to thank one of my NIST collaborators, who is Kurt Richter, and he's really our electrical guru who has taught us how to do some magneto-transport. Just to be clear, my team is typically, like, our background is spectroscopy, and so marrying it with the electrical has been fun and challenging all at the same time. I'd also like to thank Sun Lee. He is the person who made the device that we started with, and we're continuing to collaborate with him. We had a rather quick comment or a quick talk yesterday from Ferrari about Raman spectroscopy. But I just wanted to remind you that Raman is actually so sensitive for 2D materials. It is the spectroscopy of choice. Pros and cons to that. This is just an example to remind you that even sort of interesting 2D materials, such as rhenium disulfide, can have very beautiful Raman spectra, and we can learn a lot from it. I think we can all agree to most things, that Raman is very sensitive to the defects, electron-phonon coupling, and other very common things. What our team has really looked at is how Raman spectroscopy can be very sensitive to magnetic ordering. And hopefully I can convince you of that. Obviously, it is diffraction limited, and so we're not going to be able to say anything in the scanning probe sort of spatial resolution. I always like to say, people love to say Raman is a non-destructive technique. Well, I'm guessing some of you have seen this. It depends on whose hands the laser is in and what the power is set to, how non-destructive it can be. And this is, of course, very important for 2D materials. The system I'm going to talk about is actually sensitive to all kinds of quasiparticles. And the one that is most favorite for my team right now are actually magnons. Of course, we are sensitive to the typical phonons and excitons that you'll see. Typically, we're trying to avoid fluorescence. However, I hate to say we've caved, but we have. Now, we often are looking at the temperature and magnetic field dependence of excitons as well. Okay, this is sort of the larger capability. So we've coupled a triple grading spectrometer. So for those of you doing Raman, often you're using a single grading spectrometer. Of course, that's because Raman has a very crappy cross-section, and you don't want to throw away the light 3 times. But in fact, that's what we do. And that allows us to get very low in frequency space. We get on the order of about 7 wave numbers, which is 1 MeV. And that is important often for 2D materials, like we've heard of before. Some of these modes that are between the layers are really in that low frequency window. So we have from AutoCube, of course, the magneto-cryostat. In our case, we go from 1.6 Kelvin up, and we have 2 different geometries. We have the Faraday geometry, where our sample is sitting in the XY plane on top of all kinds of positioners and rotators. And then we have another version, which is called Voigt. In this case, we stand up the sample so that it's parallel to the magnetic field. This is really important in trying to assign magnons. I'll just say that. The other kind of unique piece is we have tunable lasers throughout the visible. We're using CW lasers, again, very common for Raman. We built up this capability back in our nanotube days, just to age myself. Having tunable visible lasers was very important. So we can more or less span from about 400 nanometers to 800 nanometer excitation. And then the 2 newest capabilities that we've added on are this device magneto-transport. I'm going to give you an example of that. And we finally got our spatial mapping capabilities working. It shouldn't have been so difficult, but it was. Just sharing. And I'll also say, and I think one of the speakers yesterday mentioned this, so we are hammer people, meaning we've developed a hammer and we're looking for nails. So if you guys have a nail that you think would be interesting to probe with our setup, please come up and chat with me. Okay, in this unique capability, the one thing you will never see are fibers. And we can't do fiber coupling for a few reasons, but one of the main ones is polarization. So polarization is one of the key things in doing these optical experiments. And I think I mentioned the Faraday geometry. Well, Faraday also means, of course, if you have your objective in the magnet, you have your lenses, therefore, in the magnet, and you're going to rotate the light. You're going to rotate it going down and back up. We do 180 backscatter. So you have to have a correction table for each color laser and for each temperature. Now, the temperature, the correction isn't, it's a linear thing, but if, like in our case, if we're going through Néel temperatures that are up at 150 and collecting down at 1.6, you really have to have a correction table. And so we have done, and of course we're NIST, so we do lots of calibrations. So we have these tables, and they are automated, where we can automate the polarizer so that the correction is done for us. That also then gives us our confidence in our polarization. So we can, of course, do linear or circular, right or left, and we spent a lot of time, again, calibrating and setting this polarization stuff up. Again, and that's why we can't use fibers, because we have all kinds of colors, so we're not going to be we're doing free space optics. Of course, that does annoy the safety people, but then we show them how any sort of amount of power of interest to the safety people kills the sample. So that's always our demonstration to them. We promise we're not using high power. So, of course, most of you understand that polarization is really important, and to be able to control both angles. So the angle between the incident and the scattered light, you want to be able to control. And then, ideally, you want to be able to control that angle with respect to the sample itself. When you can do that, you can get these beautiful polarization maps. So here we have Raman shift along X, and we have that theta, in this case, this is just one example, along Y. This actually is a perovskite, a 2D perovskite material. We haven't heard a lot about those. It was just an example to show you how beautiful the polarization data can be. But it is a nuisance to do good polarization. I'm just throwing that out there because it's an interesting phenomenon of how easy you think polarization should be to how challenging it actually is if you want to do it well. As it turns out, some companies, as I mentioned, I work at NIST, and we do a lot with industry when they have measurement challenges. And they were trying to do some polarization measurements at a semiconductor plant. And so we actually devised a way to use moly disulfide as the calibrant for polarization measurements. And so now there is a protocol for how to do that. And matter of fact, so the other NMI, so NIST is the National Metrology Institute of the US. Of course, there are NMIs all over the world. I think we had people from NPL here earlier. So we then do these round robins where we test the protocol to see how rigid or how robust it is actually in different people's hands. So it's just slightly, I just thought it would be interesting that we're now going to try sort of internationally to use moly disulfide, just like we use silicon, that peak in silicon as the calibrant for Raman frequency space, to use moly as the calibrant for polarization. Okay, I just wanted to show a few examples where we're actually looking at those magnons we talked about before. And just for those of you who don't know, it is a spin wave. So it's just a quanta of the spin wave, is a magnon. It tells us a lot about the magnetic order of the system. What's interesting is they often look like phonons. This is labeled Psi4 here. In a previous paper, it had been labeled as a phonon. But when you apply a magnetic field to a magnon, different things can happen. Nothing. Splitting can happen, and that's what happened in this iron PS3 case. Actually, what's kind of frustrating is when we first started this magnon work, we thought we understood a predictive way of how the magnon should respond to field. And in fact, we're learning there's lots of different ways they can respond to field. Here's another example of chromium triiodide, where in fact a feature in the Raman spectra had been labeled as a magnon, and in fact, it was a phonon. What can happen, I think most of you realize, Raman is only sensitive to the gamma point in the Brillouin zone. However, if your system has a transition where, in the chromium triiodide case, of course, we're going from into an antiferromagnetic state, we can actually see in Raman non-gamma point phonons. And in fact, that was a very rich activity going on in chromium triiodide. As you go through those transition temperatures, phonons from the K point and M point actually come in and out of the spectra. And then this other example is actually two magnon scattering. So it's yet a different excitation in these magnetic systems that we're able to see. In this case, it's coupling extremely strongly to the phonon. And so these interactions of the quasiparticle soup is another thing that we are very sensitive to and can probe, and ultimately we hope to manipulate. A very recent example, this was just published this week, chromium titanate, we're able to see two magnons. By the way, this energy scale is MeV and not Raman shift. But look how low in frequency we're seeing these magnons. And these are all different magnetic fields. A lot of exciting stuff went on in that system. I'd be happy to talk to anyone about it. I just wanted to put up these two spectra. These are not published works yet, but manganese telluride. So a lot of the things we're kind of looking after are, can we observe in Raman topological magnons? And if we can, what is going to be that signature? As everyone knows, trying to find a good way to measure and quantify topology is a big challenge. But the cobalt titanate and the manganese telluride were predicted to host topological magnons. I know when I was sitting in the back, you cannot see, but actually in this case, there's a splitting with magnetic field of this particular magnon into three. I know it's very hard to see. I wanted to put this up, and of course you can't see this either. That's counts per second. So this magnon, which does nothing with field, is 5 counts per second. This data set was 3 days. So I put that up to tell you the system has a robustness that we were very happy about. We weren't so sure about it, but again, we're able to collect for multiple days and see some beautiful things. And then we are now working on 2D perovskites, looking at the PL, and then again, applying the magnetic field and analyzing how that is changing the photoluminescence in those materials. So now, here it is. We're ready to go to electrical. So our first demonstration was to take a system that is well-known, niobium, that should be superconducting, and it's not controversial, the superconduction of niobium. And it's well understood the temperature dependence of this superconduction, as well as the magnetic field dependence. So this is resistance in Y, applied field in X, and we in fact can see the resistance going to 0 in our sample. So we felt pretty good after seeing this that at least our contacts were working, our field and temperature were what we thought that they were. So we went to Sun and asked for a graphene device. So what we wanted to do here was we wanted a couple figures for a review of scientific instrument paper, that we're writing, just kind of summarizing. So we didn't want new science. Just to be clear here, we wanted a picture for, that was the big driver, just to get something simple in the paper. So it is an HBN encapsulated graphene quantum Hall bar. And let's just start with mapping. This AFM was not done in our instrument. Sun had done that before he brought the sample. And then our first, this is how we tested how our mapping was working in the cryostat. This is the Raman 2D peak out at 2600. And you can see we have quite a it's clear where the graphene is and is not in the sample. Then we did the device characterization, just seeing how, here is our room temperature. This is gate voltage versus resistance. And then we cooled down and have this beautiful, quite high mobility in this graphene device. It's not unheard of. It just means that it was a very good device. So then we did it. We did a simultaneous measurement. So let's describe these two things. What we're looking at over here is Raman shift. This is the G peak in graphene. And we're applying a magnetic field in X. What you see is an avoided crossing, and that is called a magneto-phonon resonance. And that was most beautifully looked at by a group in France many years ago. So it's a well-known thing. Again, this was going to be a simple figure in the review. And simultaneously, we are collecting the quantum Hall measurement. We have voltage in X, conductance, and RXX are on the two axes. This particular data set was collected at 3 Tesla. You see an avoided crossing. Let me just go back there. You see an avoided crossing when the Landau level spacing, hopefully you can see these Landau levels in the red data, when that spacing is on the order of the same energy as the G peak. And so we were very happy. We were able to do that measurement. And then just to show you, HBN, which of course is in our sample, does nothing with applied magnetic field. As many phonons should not do something in the applied magnetic field, but here we have then the avoided crossing. Okay, and then this is what we really wanted, a beautiful quantum Hall fan diagram. So as a spectroscopist, never thought I'd be doing electrical measurements. Yay, we're very excited about getting this, and it's quite pretty. Now, I will say, now is the exciting time. This data set is only going up to 5 Tesla. I think I told you our magnet goes up to 9. So this data set stopped there because we actually started seeing some interesting science. 3 minutes. Okay, so here's things we're still figuring out. It appears we're able to globally dope, photodope the sample. And by global, I mean, so we use a white light source to find the sample, in the AutoCube stick, I'll call it. What we were able to do is actually to set the back gate of our device and turn on the white light and move the Dirac point, essentially what we wanted. We could dial up where we wanted that Dirac point, and it would move like we wanted. And then we could bring it back. I was quite surprised by this, as even finally we had to go call the electrical guys and be like, all right, we're doing something wrong. But so what we think is that there is some ability to do global doping. Also, we were able to do what we're going to call local, spatially resolved photodoping. And as it turns out, of course, as we then went to the literature, this has been seen before. What is the hypothesis, and I think I had it here a little bit, is that the defects in HBN, here they're labeled as positive defects, are interacting in such a way that they're affecting the conduction, the properties of the graphene boldly. Oops, sorry about that. So then we're bringing our laser in, and we're moving the laser across the sample. And what we do then when we measure the quantum Hall again, we see that we have made different regions within the graphene device. What we believe, again, this is preliminary, is that we're making a lateral PNP junction. And again, this was also a French group, by the way. They also saw this, but they did not do the quantum Hall measurements to kind of quantify or, be certain about the thing. So we can, here is just to see how pretty we can do it. Again, we're going to keep that global doping position here, and then we're going to move the other one out by dialing in our backgate. And by doing so, we're really separating the N and P doped regions quite cleanly. So also, we're actually doping it all the way across the device, which is a pretty neat thing. So here is some of the quantum Hall measurements, both with the global doping, and here it is with the spatial doping. Here is, again, a fan diagram. What's interesting, in the PNP region, we have very high resistance. So it's an insulated area. And so it is surprising, but that is kind of where we are in this sort of new science area of the electrical. And then just using a very typical edge model, we're able really to explain the data that we're seeing and the different Landau levels that we're measuring. So again, we're able to separate the P and the N quite physically and cleanly. And so it's exciting. Again, we're very new to electrical, so we're still figuring things out. Our hypothesis is on archive. Also, our group is always looking for good postdocs. So at NIST, we don't typically have graduate students, but if we're collaborating with your advisor, you can certainly come visit and do measurements with us. We do have postdoc positions available. And so thank you for your attention. I'll take any questions.
Great capabilities, thank you. We have time for one quick question.
There's one there.
Thanks very much. Are these magnetophonon coupling also observed for other phonon peaks, 2D or other, or it's on G?
Yeah, so if the energies of the magnons and the phonons are close, the chance of having more significant interaction, it goes up as their energies become closer. But we have seen it out, we've seen it, like 20 wave numbers away, we can still see the interaction. And in the cobalt titanate, we actually see the exciton interacting with both magnons and phonons. So again, the quasiparticle soup business kind of came from that.
2D or at the lower field where it resonates with the defect D peak, you also see these couplings?
Oh, no, in that case, it's really, you only see the interaction at that spacing, which is closer to the G peak in graphene specifically.